It's a great pleasure to have you all for another EPFL, CIS, and RIKEN AIP Machine Learning and AI talks. Today, we have Hideyoshi Shimodaira Sensei from Kyoto University, who's also a department chair. He's been working on the theory and methods for statistics and machine learning, and his actually covariate shift work is quite popular. I can also attest to that one. And he has this multi-scale bootstrap method that is used in genomics for evaluating the statistical significance of trees and clusters. And I guess today we will hear more about this. Take it away, Shimodaira Sensei.
Yes, thank you very much for a nice introduction. Yes, I appreciate. So today I want to talk about this topic, which is more like, statistics instead of machine learning or artificial intelligence. And recently, our lab is more focusing on, neural networks and natural language processing and embeddings. But today I just chose more, traditional topic in statistics. And this is also my favorite. So this is kind of outline. So first, I show some introduction and then example. And so, but I have a large amount of theory part, but so there are a lot of slides for here, but just I thinking I will just skip it. So, okay, so I try to explain the background and setup more here. Okay, so first let me show the kind of motivation of selective inference. So in traditional statistics, you might have been told by textbooks, like you have to prepare a hypothesis, and then after you have set up, after that, you may collect data and compute, say, p-value, or applying the statistical method to data, then report the result. Then may you reject the hypothesis or not reject or accept or something like that. So this is the traditional setup. But in reality, you usually, or you may do that, well, you may set up hypothesis and then data collection, but on the final step, if you don't have a significant result, p-value is larger than 5%, then you are not to be able to have a publication. The well-known journal like Nature or Science may not accept your result if the p-value is not significant. Okay, so you may just throw away the result, non-significant result. Or some people may do even p-hacking, like, instead of setting up hypothesis, you may first collect the data and then explore a hypothesis for which you have a nice result. Then of course, again, discard the p-value larger than 5% report only those significant one. So if you do that kind of thing, then you may usually get the inflated significance. That means more false positive than expected. Okay, so you easily have publications, but that eventually, you got the wrong result, many of wrong results, in journals. So that's a kind of motivation. So we have to do something, okay, to adjust the p-value, or you just don't do this kind of thing. But if you want to do that, you have to adjust the p-value. Then the idea is conditional inference. That means we do construct the p-value so that the type 1 error is, controlled under the condition, on the condition that you got a kind of significant result or something like that. Okay. And this has been discussed for a long time, probably. This is known as a file drawer problem. The non-significant results are maybe thrown away in the file drawer, then not on the publication. And so recently, some people have been developed, methodology called selective inferences. This is a conditional inference. Okay, so this is a kind of nice introduction paper. So let me explain a very naive example. Okay, so see, x is just a real variable, random variable, normally distributed with I just make mistake. This slide I made a little bit ago. Okay, so this is here mu, and the variance one, just this is totally wrong. Sorry. So normally distributed with mean mu, and then variance one, just this is wrong. Okay, and then null hypothesis here is mu is equal to 0 or less than 0. So this is null hypothesis. And then I would like to test this null hypothesis against this alternative. Then the p-value is, like this, defined like this. And then this probability is computed under the null, kind of null actually boundary of these two hypotheses, which is mu equals 0. Okay. Then p-value is computed like this. This function is the cumulative distribution function of the normal, standard normal. Okay, so I would like to do x is larger than this specified x, so just I have to 1 minus CDF. Okay, and I define this as a bar of pi. And just as pretend you got x equals 3, then p-value may be computed like that. So this is highly significant. Okay, but what if we test the hypothesis only when x is large enough, like selecting the hypothesis? So, for example, you discard the result if x is smaller than 2, and then only test your hypothesis only when x is larger than 2, for example. Okay, then this is kind of answer, but let me show the example first. So this is very naive. So maybe I speed up here. So this is what I said here. The p-value is the area for here. So if you observe, for example, x equals 1, then here is 1, then p-value is here. Okay. If you observe x equals 3, then the p-value is maybe here, something like that. Then this is computed like if x equals 1, then p-value is about 15%. X equals 3 is about 0.1%, something like that. Okay. And check by simulation. So if you generate 10,000 data, 10,000 x, and then compute the p-value for each of x, and then got a histogram, then under the null hypothesis, mu equals 0. Under that hypothesis, p is distributed uniform between 0 and 1. So this is what we expect. Okay, so everything working fine. Okay, and then just specify alpha, significance level equals, say, 1%. Then, I just skip here, and then probability that the p value is smaller than alpha is almost 1%. There's not exactly 1%, but this is just a sampling error of the, just a randomness. Okay. So everything working fine. But what if you select the data x equals x larger than 2, then p-value, the probability that the p is smaller than 1% is 42%. That means, for example, if you have a publication on the Nature, then if you specify 1% significance level, then only 1 of 100 papers would be wrong, and then 99 papers would be correct. But if you do such a kind of selection, then so 42%, so 42 papers would be wrong, and 58 papers may be correct. So that kind of thing happens. So this is inflated significance. Okay, so what should we do is use the right distribution, null distribution. So now we have truncation here. So the correct distribution is like a truncated normal. So if we use this normal this distribution, then p-value is maybe p-value is computed like this. The numerator is the p-value for the original problem, but we divide this p-value by this one. So this is the selection probability. So we have to divide the original ordinary p-value divided by this selection probability. So this is the adjustment. So this is very simple for this case. So if you recompute the p-value, for example, the case of x equals 3, then p-value become now about 5%. It used to be 0.1% without selection, without the conditioning. Then after this, redefinition, the conditional type of error, conditional distribution of p-value, p-value conditioned on x is larger than c, c may be 2 in this example, then this becomes uniform. So like this. And the conditional type of error becomes 1% now. So everything fine. Okay. So this is what I mentioned. So we need that kind of conditioning. So this example is extremely easy. So we got the answer immediately. But for more complicated problems, this adjustment becomes more, difficult. So for example, this is the hierarchal clustering. This is computed from the lung cancer microarray data. So people use clustering, hierarchal clustering, then you may get these clusters, okay? Then we would like to compute the significance of each these clusters. So people do this by Bootstrap, kind of resampling method. And then I have shown 3 types of p-value. So BP, this green one, for example, 67% means this cluster is, the confidence level is kind of 67. So if this is, say, for example, 100% here, then we are quite sure. But 67 maybe, I don't know, not quite high enough. And then if we do kind of adjustment for the kind of multiplicity, then that is called by the method of multi-scale bootstrap, which I will be talk about. Then the p-value becomes 94%. So, but actually, this is, I have defined 2 types of the such kind of multiplicity adjustment one. Then this red one is computed without the selective inference. So this is part of the numerator part of the p-value. Okay, numerator part, I mean. So the red one is only this part. Okay, and then, but for the selective inference, I have to adjust this one, this divided by selection probability, and then this is blue one. So blue one becomes, this is 79%. Okay, so all these values are kind of different. So we have to be careful about that kind of thing. And then for the hypothesis, like this part, so all these cells, these are non-cancer. These guys don't have cancer. So these are normal cells. Then we expect that they are forming a cluster before we do, data analysis. Okay, so we may set the null hypothesis like these guys are becoming a cluster. Okay, then it's okay to apply the testing without selective inference selection. So then we may use these red values, this everything 100 here, so there's no distinction, but so red value. But for the case like this guy, this cluster, we found that after data analysis, we never tried to make some hypothesis like these guys become a cluster before we apply hierarchical clustering to data set. So we form this hypothesis after looking at the data. So after looking at data, we may set up this hypothesis and then applying computation method to p-value for here. So this is a kind of cheating. Okay, so we needed to do adjustment of selection for this guy. Okay. So there are two steps of data collection. So first is, this is a kind of, green one is original Bootstrap probability. This is a naive confidence level. First, we have to adjust kind of multiplicity, one type of multiplicity here. And then next, we do conditioning. So these are two steps. So it's kind of complicated. This is another example. This is, the variable selection. So in this example, we had 8 variables. I forgot what those 8 variables are. And then we applied the lasso. Then we got this 6 variables out of 8 variables. So we throw away 2 variables. Then for those 6 guys, we computed the confidence intervals. Okay, so computing confidence intervals is equivalent to applying, hypothesis testing. So we have a same issue as I mentioned. So here, black ones are original, non-adjusted confidence interval. And then the other guys are adjusted ones. Then you see the adjusted ones becoming longer. That means, in other words, the black one, the non-adjusted one, is too short than expected. Okay, there are many methods, so they may compute a different confidence intervals. So this green one is too long. So then blue one is improved one, and then becomes a shorter, still longer than black, of course. And then this red one is our method. Our method is very general, so not specific to the clustering, but the method can be used in any problem. So just we use our method to this problem, then compute it. The result is almost same as blue one in this example. Okay, so now, well, I'm very slow to say. Well, I have actually 100 pages of the slide, but I will skip most of that. So now I am very slow always. So now I would like to explain the problem setup and the goal, what we would like to solve with some steps, okay? So at first, I may look at the very simplest case. So just think about we have a data vector of m+1 dimension, like say 100 dimensions. So this is a data vector. And then we assume that Y is distributed as a multivariate normal with mean vector mu, and then variance, and then covariance variable matrix is identity. And then, of course, in the clustering data or any other data, maybe not distributed like that. But for the moment, for the theory, I just assume this simple setup. And then so this is a data point. So we only got this one point. And then the null hypothesis here is this region. Okay, I said H. And then so our null hypothesis is like this unknown mu is included in this region. So this is a null hypothesis. I would like to test this null hypothesis against alternative hypothesis that mu is outside of H. Okay, so this is very simple. And so this is a generalization of what I mentioned in the very simple one-dimensional example. But now this region is any shape, and then dimension is any dimension. And if Y is very far from this region, then we would reject this null hypothesis. And then if Y is very close or even inside of this region, then we may not be able to disprove the null hypothesis. Okay, so this is the simplest setup. But in many problems, we have many hypotheses at the same time. For example, the clustering case, we have many hypotheses. So each cluster is a kind of hypothesis region. So if we have say 70, items for hierarchical clustering, then the number of null hypotheses is the number of subsets, so 2 to 70. So it's I don't know, too many hypotheses. Okay, so we have many hypotheses, and then some of them are maybe overlapped, some are not overlapped, disjoint. Okay, so we would like to test null hypothesis for each of them. So this is a kind of real situation. So we may do several adjustments, whatever, but so there are several approaches to solve this issue, but conditional we employ conditional inference approach like this. Okay, so in this setup, we actually forget about those many hypotheses, but just we may work on just one of them. That is allowed. Okay, so the problem becomes kind of simpler than controlling the many type 1 errors simultaneously. Okay, so only difference from this slides this here that so this part is the same. So only difference is here. We are going to test this null hypothesis only when data point is included in this region S. Okay, so this is a selective region. This is a kind of conditioning, if part. So if Y is included in S, then I will try to test this region H. Okay, so actually we have many of these S and then many of H. And then so we do testing for each of them. But in conditional inference, we just look at only one of them. Okay, so this is more formally I mentioned the goal. So I have been saying about setup, and then this is what I would like to control. Okay, so for non-selective inference, this selective region is actually hold the space, so there has been no conditioning. Then the p-value of this hypothesis H, so just this is my notation, this is the p-value for H, is distributed as uniform between 0 and 1 on the condition that the mu is on the boundary. So this is a kind of null hypothesis here. So this is a boundary. So for the case of the one-dimensional case, this boundary is mu equals 0. Okay. So but for the high dimension, we have this becomes a surface, of the boundary surface of the region. So this is a non-selective case. So solving this problem is kind of difficult. So I have developed a multi-scale bootstrap for this actually problem. So the difficulty of this problem is the curvature of this region. Okay, so if the surface, this boundary surface is flat, okay, then actually we can forget about high dimension. Then we only think about this direction, one dimension. So only one dimensional, simple example may apply. But actually the boundary surface is like a curved. Then this curvature is kind of related to multiplicity of testing. For example, because in a simple hypothesis, the region may be divided into two, by one surface, one hyperplane. Okay, but if you have a two condition, then we have an intersection of these two hyperplane. And if you have a those conditions, then we have intersections of those many hyperplanes. Then it's not a smooth, but it's kind of curved. Okay, it's a kind of polyhedral region, polyhedral. Then we need a kind of multiplicity adjustment. So multi-scale bootstrap method actually developed to adjust this curvature. But so I have developed this a long time ago, but recently I extended, generalized that method for this conditional inference. In conditional inference, we introduce this conditioning. So we only test this null hypothesis only when Y is included in S. So just I put this condition. Then so this conditional distribution, should be uniform. So this is what I would like to have. So then computation of this P becomes, of course, different. Okay, so let me show some examples of those problem of regions. So everything is kind of region. So this is a phylogenetic tree computed from DNA sequence data. So, so these are kind of species, and then these are bootstrap probability. So this is a kind of confidence. Okay, so this is interpreted like, we have a data space, and then each region here may be corresponding to, some cluster appears, or here first they define that each region corresponding to each region is corresponding to tree. Okay, so this particular tree shape is a kind of region. Okay, so there are millions of these shapes. So there are millions of regions overlapped. For example, this region and then this region overlapped. Okay, and then some intersection part may be corresponding to for example, this cluster or something like that. So each tree or each cluster, everything is kind of region in the data space. So this is a kind of problem of regions. For the variable selection is the same, okay? So kind of data space, or actually this is I said data space, but this is also interpreted as a parameter space, okay? So you have computed the parameter. This mu hat is actually, I forgot, just here, beta 0, first, beta 0 is ignored. I mean, just subtract the means for the y and x, so we can forget about beta 0. So the regression coefficients is summarized as beta 1 and beta 2, so only 2-dimension. So, everything is drawn in the 2-dimension space. So, data point is kind of summarized in this parameter space. It's a kind of sufficient statistics. Then, so each region here corresponding to the, model selection. So here, this model is selected. And then these two regions corresponding to this linear model. And then the outside is corresponding to this quadratic model. So model selection is also the problem of regions. And this is a kind of multiple comparison problem. Here, later I may talk about this example. This is a phylogenetic, tree of life. That is problem. So we may compute a score, actually likelihood value for each trees, and then choose the tree with the highest likelihood value. So it's the same as a model selection. And then so we may compare the likelihood value of these models. But we have many models, so this is kind of multiple comparison. So we may compare, we may adjust the multiplicity of testing, because this is the tree of highest likelihood value. And then so if you subtract this guy and then this guy, so this is a difference, then this is not just actually the difference of two likelihood, but actually this is a kind of maximum of these differences, because we compared each tree with the maximum value of those whole likelihood. So we need to adjust this multiplicity. So this is actually the thing I mentioned. Okay, so each comparison corresponding to the flat surface, and then dividing the whole region into two by the flat, so it's half space. Okay, but we have taken the maximum of that. So this is corresponding to the intersection of these half space. So this becomes actually, in this case, polyhedral complex cones like this. So, okay. So this is kind of curve, okay. So these are more simple case, smooth curves. So if the region is curved like this, then we have to, do adjustment. So the theory of multi-scale bootstrap, the algorithm I will mention a little bit later. First, I developed for this smooth surface case, but in reality, I often face this kind of non-smooth boundary, with singular point, but still it looks like curves. So I had to develop a kind of generalization of, this, theory. So, if this is a smooth surface, we do simply think about Taylor expansion of the boundary surface. Then we may think about, mean curvature or that kind of classical geometry, values we can use. But if this is not a smooth surface, then all those classical ideas cannot be used. Then I had to develop another theory, but still it works. So the method still works. Okay, so this is kind of too much now, but okay, just I wanted to mention. Okay, this is another example of region. So this is the selective sets for lasso. Okay, so in lasso, this is the same as model selection, as I mentioned. Okay, so each region corresponds to the model. So this is selecting model 2 here. Then this is selecting variables, selecting variable 2. Here, selecting variable 1 and 2. Here, selecting variable 1, like that. Okay, so this is a model example of model selection by lasso. Okay, in lasso case, people have been developed the methods, a lot. So people, know this kind of thing. So this is a selective region in lasso. So everybody knows here. Okay. So now I would like to talk about our method. So our approach is called multi-scale bootstrap, in which we change the sample size or data size in the replication. Okay. So here the original data with sample size n. So this could be something, anything. But n is like 30, for example. If you have 3 students in a classroom and then computing some grades, okay? So and then trying to compute say average or variance or whatever. Then in such a kind of example, n is just 30. Okay, this is very easy. And then in Bootstrap resampling, we generate this kind of simulated data replication, replicated data by randomly picking up those elements, randomly copying, allowing replication. Okay, so and then usually this is n prime is the data size of this replication. Okay, so n is original. So usually, of course, n prime becomes n prime equals n. So n prime also 30. But of course, we can change n prime to any value because this is kind of just a for loop in a program. So if you can change n prime to say 50 or 5 or whatever you like. Okay, but still you use n prime equals n usually, of course. And then the confidence value by doing this method. Okay, and I forgot to say that. So and then keep doing this procedure many times by using the pseudo random number, say 10,000 times, and then count the frequency, how many times you observed the same result as before. For example, the clustering, you may got the 10,000 trees and then count how many times the same cluster appeared in that kind of 10,000 trees. So very easy. Okay, so for example, you may got 9,000 trees with the same cluster with the original data, then this becomes a 90% sure. Okay, so that probability called the Bootstrap probability is interpreted actually kind of Bayesian posterior probability under some flat prior. So we say that, okay, this is a Bayesian. Okay. And then, as I said, we can change n prime. Usually people do, smaller n prime for faster computation, but we don't intend that. And then our theory says that n prime should be minus n. It's very strange, but if we compute the Bootstrap probability with negative sample size, then that gives frequency p-value, adjusted p-value, okay? So if the boundary surface is flat, then these two guys, Bayesian posterior probability and then frequency p-value are equivalent. But if the surface, as I said, boundary surface is curved, then they become different. Then for frequency sense, we should use minus n. So this is a theory. Of course, we cannot compute the minus n. So we compute the p-value, bootstrap probability for several positive values, say 50 or 100, whatever. Then do extrapolation of those probability value to the minus n. Okay. So this is the algorithm. So very easy. This method has been used quite a lot. Okay, so I'm happy about that. Okay, and then you see the values are kind of different, as I said. So we should care about this kind of thing. Okay, and okay, this is okay. So let me talk about a little bit algorithm more. So this is, as I said, this is a model. So Y is distributed as normally distributed with mean vector mu. And then Bootstrap resample is modeled like this. So Y star is now Bootstrap resample here, these blue guys distributed around Y, okay? The original data is distributed around mu, okay? But we only have this 1 point. We don't know mu. So we know only Y. So we generate a data set around Y. Then we got the many Y stars, okay? Say maybe 10,000 Y stars. And then count how many times Y stars are included in this region, okay, like this. So this is a computation of Bootstrap probability. So this is, if B is large enough, say like 10,000, we interpret this as probability. Okay. Now sigma squared is here. Okay. So we may change sigma square variance to any value. So if you change n prime, that's kind of equivalent to changing sigma squared. So original Bootstrap should use sigma square is equal 1, but we may choose use say 0.5. If you increase the number of samples twice, then that's equivalent to half of the variance, something like that. So we may compute several these guys and then extrapolate these guys to sigma square equals -1. Okay, that's our algorithm. Okay, but of course, in reality, we do non-parametric bootstrap, instead of those normal distribution. Okay, then we just assume that there is a kind of transformation for which, some data distribution converting to, normal distribution. So this is only approximation in reality, but just we pretend there exists such a kind of nonlinear transformation. And in the actual computation, we don't have to know this Fn. Then just we keep working on this part, non-parametric bootstrap. So computation is, very easy anyway. Theory looks difficult, but computation is very easy. Okay, so this is the main result. So this looks complicated, but let me explain a little bit. So this part, okay, this part is bootstrap probability, as I said. Then first, use this inverse function of CDF, tail probability. So this part is kind of Z value, we say. And then strangely, we multiply sigma. That means square root of sigma squared. Then we define this guy and extrapolate this guy to sigma square equals -1. Then we got this guy. And then, of course, I apply this CDF again to this brings back to p-value. So this numerator part is the original multi-scale bootstrap, which is a non-selective inference version of adjusted p-value. Okay. So this is the extrapolation to -n. That's what I mentioned. But now we would like to compute, also the selective inference. Then we have a now numerator part. So this looks also kind of complicated, but this part is same as here, and then this part is kind of bootstrap probability for the selection probability. So we also need to adjust this selection probability, and then we have just proven that this part, this denominator corresponding to kind of selection probability adjusted those, curvature adjusted version of the selection probability. Then this, fraction gives the selective inference version of p-value. Okay. And if you compute that p-value, then that controls this probability. Okay, so this is the conditional probability, So p-value are smaller than alpha, conditioned on y is included in the S is alpha. So this is what we would like to have. So this is a type 1, conditional type 1 error is equal to alpha. So without a conditioning, the unselected selective inference version, non-selective inference version of P is controlling this guy. So without conditioning, this controls type 1 error. So we now have 2 versions. Okay, so let us see examples. Okay, so there are many p-values. So just look at this particular cluster. Okay. So the data size was about 900. Then I specified n prime to these 9 values somehow. Then sigma square is defined like this. Then the B was 10,000. Okay. I'll just forget this guy. Okay. Let me a little bit. Okay. So in this case, let me explain this again. So in this case, this region corresponding to cluster. Okay, so this region corresponding to, we found the particular cluster like this guy. So now we are looking at this particular cluster. Okay, so now data point is inside of this region. That means we observe that cluster. Okay, so we test that cluster only when data point is inside of this region, because otherwise we don't observe that particular cluster, so we don't care that cluster. We never test it. So the null hypothesis we test here is that mu is included in the complement set of this cluster. So that means hypothesis region is a complement set of this S. So S is a selective set, that is a cluster. So complement of S. So that means this cluster is not true. Okay, so we test that null hypothesis condition that we observed Y inside S. Then if this null hypothesis is rejected, we mean that cluster is kind of true, significantly true. So it's very strange setup. In statistics, we don't usually do that kind of thing, but we are now doing that. Okay. So this is a computation. Okay, so just forget about details, but look at so this count how many times we observed that particular cluster in the 10,000 simulation. So we have different values for different n prime values. Then converting this guy to first p-value, just dividing this value by b. B is now 10,000, and then converting this value to this psi. Then this is the plot of psi. So we have a theory that this is almost linear. So we can prove that. And then, so actually we observed that. So this is almost linear. And then this is a sigma square. So this is psi. So just simply linear extrapolation, okay. But here we have used a little bit improved version. So maybe I fit a quadratic curve here. And then extrapolate this guy to minus sigma squared minus 1, then just read this value. Okay. So this is what we want. And then applying the CDF function to this value, we get the p-value. So that's the computation. This is interpreted also like this. As I said, this is almost linear. So this is a linear. So beta 0 is, okay, this value is beta 0. And then beta 1 is this slope value. So in this particular example, beta 0 is, kind of this value. This particular value doesn't have not really makes meaning, but and the beta 1 hat is minus 0.5. This is slope is this way. Okay. And so, but interesting, our theory says that these two values has a geometrical meaning. And then this value is called the signed distance. And then this value is curvature. What this guy is, signed distance is a distance from boundary to this surface. And then the curvature is this guy. So the negative value means, now hypothesis is outside. So looking from this side, curved, kind of concave. Okay, concave is negative. If it's convex, it is positive. Okay, and then this is if this y is on the boundary, the sign distance should be 0, but now it's kind of far from this boundary. Then the value was kind of 1. Okay, that's an interpretation. And okay, it's almost a time. I want to go. So I want to show example more, but okay. But this is a kind of theory, so important. So in mathematical statistics theory, we have had that exact formula. So this is the Bootstrap probability. So if we change the scale sigma to not to sigma squared, then the assigned distance is, it's the same as rescaling this everything. Then distance is scaled by this, and then curvature is scaled by this. So this is the formula for the general Bootstrap probability. And then if we applied that transformation, as I said, then we go to this formula. Okay. So this is a kind of proof. Then, okay, we change the sigma, then we change like that. Then what means sigma scales -1? So let me explain a little bit. So if we change the sigma scale -1, that's intuitively flipping the curvature to the other way around. Then if we change the sigma squares -1, then beta 0 plus beta 1 becomes beta 0 minus beta 1. Then we can also prove that the frequentist p-value is expressed like this. So this is a brief summary why the multi-scale bootstrap adjusts the curvature, but not yet the selective inference part. So explaining why selective inference is that formula takes a little time, but selective inference computes the denominator part. Okay. Okay, then for the selective inference, computation is easy like this. Then everything is almost intuitive. Then we got the selective inference version of p-value. So it's computation itself is very easy. Okay, then we have adjusted version. Okay, so so this is it's almost a time, and then I was just keeping up. So now I have shown PV hierarchical clustering example, but everything is almost the same for the phylogeny. So this itself is also kind of long story, but let me show only this example. This is a phylogeny of mammals. Okay, so we have 15 hypotheses like that. So if we apply the original Bootstrap, p-value is like that. So if we have a 5% threshold, only these two guys are not rejected, and these guys are rejected. And interestingly, so this tree is rabbit is closer to mouse. This is a conventional tree. Biologists believe that this is true. This tree was rejected, and then this unusual tree was selected, and then this was actually once published in Nature, late 1990s. Because this is a new discovery for them. But later we found that this is wrong because we have collected more data. Okay. And then, so we have developed a safe method, which is, called a multiple comparison, in all the statistics. Then we have recomputed the p-value. Then now confidence set of trees becomes like that. So this is safe. The true tree is now included. So this is safe. But this is kind of conservative. So too many trees are included. So biologists are not happy about that. So, if we apply the multi-scale bootstrap I mentioned, so true tree is included here. Still, the number of selected tree becomes smaller. So we are happy. So this is a kind of optimal. Okay. So, as I shown, the results are kind of different. Okay. So, well, this is maybe too much, but we have computed the regression, the confidence values for trees. Also, this is an example for the lasso, as I mentioned. Then for the case of lasso, I have explained already. But there are other types of more complicated version of lasso. It's not a lasso anymore. Then we cannot define these regions anymore, but we only have got the result by just computation. Okay, so even in a kind of complicated selective region, we can apply the method, of course, because we don't care about those in a particular case. We just count how many times we observe the result by simulation. Then we can, compute, those p-values, confidence intervals, not only for lasso, but for complicated one. Okay, so I have a bunch of theory, but just I want to skip everything. Then it's almost a time. So now that's it.
Thank you, Shimo Daira Sensei. So I guess there are some questions. I also had a question, maybe one or two quick questions. One is related to this p-value quantification. So we try to understand some uncertainty about some of the variables that we're picking. Have you considered maybe using some of the recent methodologies based on generative adversarial networks to try to maybe computationally estimate some of these posterior distributions to come up with some of these, let's say, confidence bounds on the variables? It's maybe slightly out of the presentation, but a bit related.
Could you say again which method you use for the
so for uncertainty quantification, there are ways of modeling distributions using generative adversarial networks.
I see. So of course, if you have a specific model, then based on that specific model, then you could compute a built-in confidence value, sort of. Okay. Then that is fine, but well, that may not quite good if the model itself is not really real, good approximation to the reality. Okay. So, or even you may have a situation like a hierarchal clustering. You don't have a built-in such a kind of confidence value. Okay. That means you have some method. Okay. Then you got the data, then you feed the data to the method, then you got the result. You got just tree or something like that. Okay. Then in such a case, we have a kind of external method to give validation to that result. Then, so the Bootstrap probability, for example, gives that. So because that is a very simple simulation, just generate many data set and then compute, apply the software, to the data set, 10,000 times, and then got the frequency. So very simple. So such a kind of, have the generality we have, that means, okay.
I think that this is an interesting point that in this particular case, we kind of lose this rigor and somehow certification that comes from this careful analysis and mathematical approach. So I think maybe some of these trade-offs would be interesting to consider, at least because at least in your multi-scale approaches, I really wonder how you would even attempt to do this with some of these GANs and so on and so forth. The second question I had was, again, maybe something related. These works on variable selection with knockoffs. I think Emmanuel Candez was pushing this particular direction also quite a bit in terms of variable selection. Did you have any comments on this?
Okay, that's a nice point. Well, so when naively applying the Bootstrap to the case of GAN, of course, may not be possible, of course. But, for example, variational autoencoder, for example, you have an internal representation, this is the input, internal representation that is kind of normally distributed. Then you have an output. So in such a case that you don't have to fit the data many times here, but you have an internal representation on which literally you assume that is normally distributed. Then in that space, you can play with this kind of thing. And then, so you don't have to refit in those whole neural networks many times, maybe just fit the data once and then play, in that, this internal representation. So that's very fast. That should be very fast.
Oh, that's correct. That's a good point also. Any questions for Shimodaira Sensei? I think there is one question. It would be great if you could write your question onto the Q&A.
May I speak? Do you hear me?
We hear you.
Yeah. My question is that how much does your argument depend on the normality assumptions? Actually, you see, the same probability distribution can be represented in different parameterization. And the parameterization, depending on the parameterization, confidence interval is different.
Sure.
So how does your argument this today depend on the normality assumption?
Thank you very much. The theory itself is heavily depend on the normal assumption, this model, you know. So if the Y is not disputed like this, then we have to develop another method. And then once I long time ago developed a method for exponential family, that's a generalization of this model. That is kind of equivalent to saying that this I may depend on mu, you know. So this in general, this because sigma, then sigma may depend on mu. Then things become very difficult. Okay, but you know, in a rough approximation, around the true parameter, you know, if the data point is not very far from the true parameter, then that sigma, in general, this is just a sigma, right? Sigma doesn't much different from the true sigma, okay? Then you may do, you know, just a linear transformation, whatever, to get the sigma equals identity. Then, so as a rough approximation, you know, it's okay. And then, so first of all, of course, the distribution is not exponential family or whatever, but often the case that, for example, any maximum likelihood estimator is asymptotically normally distributed. So in anything, any setup, like, you know, not necessarily maximum likelihood estimator, but most of those statistics is roughly distributed kind of normal, you know, and some constraint concept. So just I pretend that, you know.
I see. I understand your position.
Yes. And then let me say that. So, you know, this, you know, and then, you know, even if the distribution is not really normal, then if we make some nonlinear transformation so that transforming this variable to another space, then if transformed variable is normally distributed, this theory works. And then without knowing that F, that means that the method is very robust, actually. So I experienced that, you know, method works very well, you know, even under, you know, non-normal case. That's my experience.
And another question is, I don't know the negative sample size case. Would you explain a little bit about the negative sample size case?
Negative sample size is only kind of theoretical. So we compute those p-value for only positive sample size. For example, if n equals 30,
and
then
how do you estimate then?
So again?
How do you estimate then from this positive sample size to?
Not, we just specify. For example, if n equals 30, just I choose n prime equals, say, 50, 100, or 15. Just I specify 4 values, okay? Whatever you like. And then compute the bootstrap probability for those 4 n primes, okay? Then, you know, using these 4 bootstrap probability, you can extrapolate those probability to n prime equals minus n.
You do that. I see.
So it's not the estimation, but you just specify.
I see. I see.
Thank you very much for that point.
Thank you very much. Very interesting.
Thank you for the question.
Can I also ask one question? So it's nice to have an asymptotic theory. So you have n to the power of 3/2 or something like that.
Yeah.
That's great. But in practice, so I want to know your experience. So given some slightly more complex hypothesis, so is this theory still work with reasonable number of n?
It's of course depends, of course. So I don't really apply this method for for the case of neural network or such a kind of extremely many parameters and then extremely a lot of data. I don't know, but for the moderate case, classical statistical setup, then it is okay if, for example, n equals say like 100. And the number of, not necessarily you don't have really parameters, but in the case of regression, if you have say 30 variables, or then if you have 1,000, n equals 1,000, for example, then it works. Okay, but if you have only 30, n equals just 30, then maybe it don't work well. Yes.
Okay, thank you. That's great news.
Well, thank you very much, Shimodaira Sensei. So this concludes our session.
Thank you very much. Okay.
Have a great evening in Japan. And
okay, see you sometime.